Thanks, Martin. Hi, I'm Barry Sankey, G7 RWY. I'm very pleased to host the first session this morning, and to get things off to a start, as Martin was saying, we've got Chris Saunders joining us from SSTL to give a talk on SSTL, LEOs, MEOs, GEOs and beyond. So this is looking into the future. So, Chris.
And while he's there, just to embarrass him, I won't sit in the front row and glare at him. So, over to you, Chris.
Thank you. Yes. Sorry. Okay. Set it up. The one at the bottom, I think.
That one?
Yeah, no. That's it.
Is it?
Yeah, it is. Perfect. Thanks. Well, good morning, everyone. My name's Chris Saunders. I'm from, Martin said, from SSTL, just down the road. And today, I'm going to give you a talk on what we are doing, as it says on the screen there, in low Earth orbit, medium Earth orbit, in GEO, and then beyond GEO. So, what I'll talk about today is just a brief update on SSTL, quick overview of who we are, and then some of the major projects we've got going at the moment. So as Martin's already mentioned, DMC3, but I'll also talk about some of our other missions, Carbonite, Novasar, FormoSat-7, as you can see there on the screen. And then I've got a few slides at the end on some new projects that we're doing that are a bit different from what we've done at SSTL before in the past. So one called Twinkle, and then I'll talk a bit about what we're doing regarding the Moon and a lunar communications program we're doing with the European Space Agency. So for those of you that don't know, I'm sure most of you do, but SSTL, Surrey Satellite Technology Limited, we're a medium-sized space prime contractor, and we're here in Guildford, just down the road. And we design, manufacture, and do the operations of small satellites, as well as we provide equipment, subsystem sales, and we do services. There's about 500 of us here in Guildford and in Borden. And we've got a small outfit in Colorado as well. And we do kind of stuff from first concept, back of the envelope, trade-off studies, which is the kind of area that I work in, through to in-orbit operations, data processing. And the company tagline is changing the economics of space, and that we have been doing that for, well, ever since the company's been started, really. We provide high performance at low cost. And here's some numbers. We've had a satellite that's UOSat-2's still operational, been in orbit for 30 years. We've launched 47 satellites. For example, you know, our smallest satellite's 3.5 kilos, was the CubeSat. Over half a ton was Jovi, so we do a whole range of different systems. Average about 2.5 spacecraft per year over the lifetime of the company. It's quite an enviable track record. So I'll give you a quick update on our major projects. As Martin's already mentioned, DMC3. It was the first, really, for commercial Earth observation. So there's a Chinese company, 21st Century Aerospace, or 21AT, has leased 100% of the imaging capacity for us for 7 years. So they handle all the tasking, the data download, and the image processing. And 21AT, a very successful company in China, using Earth observation data for urban planning, for agricultural assessment. They do lots of different services that they've built off the back of Earth observation data. And the quality of the imagery they're getting from DMC3 is really helping them to build their business and to expand from the medium resolution data they had before into this high res. There's some technical details on the left there, which you obviously don't have to memorize every number there, but the key pertinent points are it's extremely agile spacecraft, so we can cover a lot of swath with the imager. It's a meter resolution in panchromatic, but it's also got a 4-meter multispectral 4-channel capability as well. We can, as it says there, we can do over 100,000 square kilometers throughput per day per spacecraft. And of course, in the constellation, there are 3 of them. So you're getting onto 1/3 of a million square kilometers a day. And you can see that the spacecraft are being used quite hard already. So in May this year, it was almost 14,000 images captured. And that was over 7 million square kilometers, which is about 17 terabytes of data. So they're quite a significant throughput on these spacecraft. Here's some imagery. You've seen these two already, but yeah, we are getting a significant number of images down, but there are limitations on the ones that we can show you, I'm afraid. So you've seen these two already. But as Martin showed you in the picture of London at the top, the resolution and the detail and the sharpness of the imagery is really, we're very pleased with that. So it's really, and so is the customer, thankfully. Alongside, you saw this picture before, but alongside the 3 DMC satellites last year, we also launched another satellite, which I've circled down here, which is called Carbonite. And that was a satellite that we built ourselves as an experimental demonstrator. We funded it, built it in-house. It was an experimental satellite, built to see really how fast and how quick we could do something that would produce some useful data. So using low-cost optics and sensors, using spare parts, using as much off-the-shelf stuff if we got flight spares from previous missions, etc. The key point is we actually went and bought a commercial, you can see on the bottom there, a commercial Cassegrain astronomy telescope, repackaged it, put a commercial machine vision sensor on the back, and that was the main imaging payload. And it was built from the project kickoff to the end of the flight readiness review was just over 6 months. And that was, as I said, launched on the same PSLV spacecraft. And here's an image from that. This is of Dubai. So as you can see, it's obviously it's not the same spacecraft as DMC-3, but it's a significantly different price point than those kind of spacecraft. It's doing a different application. So we built this to try and show that you can have low-cost volume manufacture to produce sort of useful Earth observation data. And we're very pleased with that, and we're currently working on a follow-on. NovaSAR, as Martin mentioned, is a SAR spacecraft, synthetic aperture radar, in S-band that we're building at the moment. This is the flight model here. It's a collaborative project with Airbus in Portsmouth. So Airbus responsible for the payload. We're doing the platform and the mission operations. It's got 4 modes. So there's a strip map mode, ScanSAR, and then we've also got a maritime mode, which is deliberately, for those of you who know about SAR, it's deliberately ambiguous. So it's not producing an image, but it tells you if there's something there or not, a ship. So the advantage of that is that we can get a very wide swath of over 400 kilometers on the ground, which is very useful for maritime surveillance. It's about half a ton, so it's quite a big spacecraft. And we've got a launch plan for this towards the end of the year. And it's, as you can see, with the kind of numbers we're here, it's a sort of analogous. It's a synthetic aperture radar version of the disaster monitoring constellation. So it has similar type applications: agricultural monitoring, flood management, ice detection, maritime surveillance, as I've mentioned. So we're quite excited about this. Obviously, this will be our first SAR spacecraft. Another big project we've been working on is FormoSat-7. Now, this is a joint mission between Taiwan and the United States. It's actually a meteorological mission. But we have been contracted by NSPO in Taiwan to provide the platforms onto which the Taiwanese and American payloads are carried. And this mission is interesting. It measures it measures radio occultation of signals from GPS satellites as they get bent through the atmosphere. So as the FormoSat satellite is passing around the Earth, these GPS satellites will disappear below the horizon. And as that happens, the signal gets bent, and the measurement of that angle, you can use that to tell you how much water is in the upper atmosphere, and that's a very useful parameter for weather forecasting. So we've built 6 of these satellites, and they're going up hopefully on a Falcon 9 towards the second half of next year. As you can see, there's one in the bottom here. It says has deployable sun tracking, 2-panel solar array. Departure from our usual stuff is not in a sun-synchronous orbit. These are in a sort of medium inclination inclined orbit. Now, Quantum. This is another big project that's just really ramping up now. It's a geostationary satellite. It's for Eutelsat. Airbus are the prime contractor. We are the contractor for the platform. Airbus are providing the payload and the prime. And it's for Eutelsat. And it'll be our first GEO platform. The key thing about this mission is that the flexible communications payload, you can reconfigure on orbit. So if the customer demand changes or you want to change your operational longitude of the spacecraft, we can reconfigure the payload. And you can see on the front here it has a phased array type antenna system here, and there's also another phased array feeding a reflector on the side here. Launch is planned for 2018, and it is extremely big. It's 3.5 tons, and it has over 5 kilowatt power system. So it's a long way from the old SSTL spacecraft of the 50 kilos. And a 20 watts orbit average power. This structure you can see on the right here is the central thrust tube. This is 3 meters wide and 3 meters high, and a meter wide, and that weighs over 100 kilos and is purely there to carry the propellant tanks for the mission. So just the bit of the structure that carries the tanks weighs more than a DMC class satellite. So it's a big beast, and it's going to be a big project for the next couple of years. Galileo, as I'm sure you know, we've been building the payloads for the European Commission Galileo navigation system, and I'm happy to say that we shipped the 22nd and last payload to the prime contractor OHB in Bremen in June. That's the last unit we were under contract to provide. We're currently bidding for, there's a third works order contract. And now there's 10 Galileo satellites with our payloads on operating successfully in medium Earth orbit. And the next launch is November this year. It's a pipeline of launches that are coming through. And that's going to be the first one on Ariane 5. We're going to launch 4 at once. Previously, they've all been launched on Soyuz 2 at a time. So that's going to be quite interesting. And I think it's fair to say that Galileo has been an absolutely massive project that has taken a huge amount of effort from an enormous number of people over periods of years. And you can see some of them down here. And yet, of course, although we've shipped it, it hasn't finished. So there's still system testing at OHB with the remaining satellites. We've got to verify them, the validation activities, there's in-orbit support. So it goes on and on and on. But it's been an enormous project, but a very successful one. Touch on a couple of our smaller spacecraft. We've got 2 under manufacture at the moment, CAS STSat and ALSAT-1B. Both of these are collaborative programs we're doing with foreign space agencies. So CAS STSat is being done with Galam of Astana in Kazakhstan, and it's part of a training program that we're doing for the Kazakhstan engineers. So they're here based in Guildford now, working with us, and we're training them, and they're helping to build and design the spacecraft. And it's going to be a 100-kilo Earth observation platform carrying medium-resolution multispectral imager. The other one is ALSAT-1B, again, a collaborative thing that's been done with the Algerian Space Agency this time. And that's going to be our traditional SSTL 100 platform, which was used on disaster monitoring constellation, and that has a multispectral and a pan-chromatic camera. And again, there's going to be a training program for the Algerian engineers. So that's a quick blast on what we've been doing this year, but now I want to talk about some new things that we've got coming in the future. Now, so traditionally, virtually all of our spacecraft have looked down at the Earth, whether that's for remote sensing, Earth observation, taking pictures, or for communication, so providing a radio signal back to Earth for someone to use. We've got 2 things coming that we're doing at the moment that are a bit different. So the first one is a mission called Twinkle. This is going to be looking up. So this is a mission we're working on for commercial astrophysics and science spacecraft. And that's going to be producing spectral information on the atmospheres of planets, of exoplanets around other stars. So that's quite an exciting concept, and I'll tell you about that. And then we're also building, as I said, we've got spacecraft, or we're building spacecraft for low, medium, and geostationary orbit at the moment. But as I mentioned in the title of the talk, we want to go beyond Earth orbit. And at the moment, we are starting up something called Lunar Communications Partnership with the European Space Agency. What we're trying to do is provide a commercial infrastructure that will support the future of space exploration in the inner solar system. So that's quite exciting, and so I'm going to tell you about that as well. So Twinkle. Now, Twinkle is not actually an SSTL mission per se. It's actually run by a company called Blue Sky Space, which is a spin-out from University College London. And the aim of what they want to do is provide data which will help understand the composition and structure of exoplanets. And actually, exoplanet science is one of the biggest current areas of research in astrophysics as a whole. And requests, for example, requests for exoplanets observing time on the Hubble Space Telescope are heavily oversubscribed. There's more demand than supply at the moment. So Twinkle aims to be a commercial astrophysics mission that will sell observatory time on the satellite in a similar way to how large ground-based telescopes operate. So the large telescopes on the ground at the moment, they're paid for by research funding bodies and grants to academics. And Twinkle wants to operate in a similar way, providing science, effectively science as a service. So the spacecraft itself that we're working on with them, as I should say, SSTL, we're responsible for the platform for Twinkle and the spacecraft, and Blue Sky Space have a separate payload consortium which is designing the instrument. But the spacecraft itself will be a modified SSTL 300 as was used by DMC on the DMC-3 mission. So you can see that it has this similar shaped body, but a different solar panel configuration. The payload itself is going to be a half-metre diameter telescope, which is bigger than what's on DMC-3. And instead of having imaging CCD, it's going to carry an infrared and visible spectrometer. So it's providing spectra rather than an image. It's in a dawn-dusk orbit, which is why we have these particular solar panel arrangement, and it requires the spacecraft to very accurately point at a star for a long period of time. We have to observe the star as the planet transits in front of the star, and so the attitude control and the pointing stability on the spacecraft is a critical parameter. So as well as the spectrometer, inside the telescope there's actually a second sensor, which is a fine guidance sensor, which is actually, so the payload is then used as part of the attitude control loop, or will be used in the attitude control loop when we're observing. And the payload study is being completed now, and we're sort of halfway through a mission level definition study at the moment. And you can see that using Hubble, it only covers around half a micron of wavelength. You probably can't see the numbers here, but if you take my word for it, that's about half a micron is all the coverage that Hubble gives them. Whereas Twinkle's aiming for 4 or 5 microns of coverage, so it'll extend the spectral knowledge of exoplanets significantly into the infrared, which is extremely useful for looking at the composition of these planets and finding out if there's potentially any of them are life-bearing. Now, on to the moon. Now, as we know at SSTL, and you guys know as part of AMSAT, small satellite technology, making a satellite small but still useful, has really powered this explosion of new activity in low Earth orbit. And there's a whole bunch of startups, commercial ventures, universities, amateur guys, everybody doing stuff in low Earth orbit. But trying to do that when you want to go beyond Earth orbit becomes increasingly difficult. So you've got a restricted mass, a restricted power, and a restricted volume on the spacecraft. But on the other hand, there's usually, if we want to go beyond a circular low Earth orbit, that usually means you have quite high delta V requirements, you have a very high Earth to spacecraft range, and so transportation and communications are the two main limiting factors for small spacecraft and small spacecraft systems to be used for space exploration. So, with that in mind, and we want to try and do something about it, we have started a partnership with Goonhilly Earth Station down in Cornwall. It's a private company that have taken over the old British Telecom site down there. And we're working in partnership with them and the European Space Agency in a pilot phase activity that's going to try and help beat these two problems, which is providing a transportation and a commercial communications, and in the future, a commercial navigation infrastructure in the solar system. Now, the long-term vision is that we're doing that because communications and the related services such as navigation are actually the glue that holds together all the future exploration activities. So whether you're at an asteroid, a near-Earth object, the moon, or your Mars, and whether you want to do science, or you're doing manned exploration, or you're doing resource extraction, asteroid mining, or you're simply tech demo, and all the things you can do with that, the landers, rovers, penetrators, manned bases, you want to teleoperate a rover, all these things require communications, and you need to know where you are, and you need to know where you're going, and then you need a way of being able to tell your operations center that that's what you're doing, or you've got to send payload data back, etc. So we see that actually this is, Martin described this the other day as not the glory stuff. Right? The glory stuff is in the blue boxes there, the science. We're not trying to be the people who find the water deposits at the South Pole of the moon, but we're quite happy to be the people who communicate that back to Earth. Right? And we think that actually there is a commercial market in providing these kind of services to the people who want to do the stuff on the right. So that's the kind of the vision and the basis for why we're doing it. So what we're doing about it is, as I said, we've entered this partnership for explorations program. Now, ESA, the European Space Agency, is currently investigating ways that partnerships with industry can benefit space exploration. Now, this is it's not exactly the same, but it's similar to what NASA have been doing in the US with the Orbital and SpaceX COTS program, released by the ISS. NASA is using the industry to provide it with a service that it can't provide itself, or it can get in a more cost-effective way by using some other service provider. And so what ESA are trying to do is they are supporting selected initiatives. So there was a call for ideas and a bidding process, and we've been successful so far. And ESA are currently looking at 8 possible partnership schemes with different industry around Europe. We're one of those 8. And as I said there, the quote from David Parker, who's the new Director of Human Spaceflight and Exploration at ESA, they're looking at it either as a potential future customer or a business partner, and how it can benefit them, but also be commercially viable. And so in our partnership, as I mentioned, we're with Goonhilly and ESA, so we're responsible for the space side of this, so the development of the spacecraft, providing a launch, coordination of the payload design. Goonhilly, I don't know how much you guys or anyone of you know about Goonhilly down there. Probably you know that it's got an enormous number of very large capable antennas, and we're proposing to use their Goonhilly 6, which is a 32-metre antenna on a full ASL mount. I think it weighs about 500 tons. It's an enormous beast. It's being upgraded to X-band, which is going to be what we're going to use for our primary Earthlink. But also Goonhilly has very good terrestrial connectivity, major internet trunk route there for the transatlantic cables. So we want to provide a sort of mission operations centre here that can be that can also connect into a global network. And ESA, as part of the partnership program, they are providing us with facilities help, expertise. So they're actually doing, as part of this program, they've been doing some work for us for a change. So instead of us doing work for them, they've actually been providing us with some info, helping us with technology transfer, building international connections, etc. This is our sort of long-term roadmap. It's sort of showing how we foresee the future of what we want to try and do. Now, in the middle here, we have what we're currently doing now, which is our Partnerships for Exploration program. And we want to do this Pathfinder, a first mission called a Pathfinder, which I'll talk about in a second. We believe there is a market in customers for doing technology demonstration, low-cost, high-value science, so CubeSats, nanosats, and supporting landers. There's quite a stream of landers aimed at the moon over the next few years. We're providing as a service, we aim to provide a local UHF communications link between assets at the moon, X-band back to Earth. But over time, we foresee that if this is successful, we can start transitioning to a full service provision. There will be more going on at the moon, the habitats, both on the orbiting and on the surface, more landers. And eventually, we want to build a constellation of spacecraft around the moon. Goonhilly have plans for building on what they've got in Cornwall and creating further deep space network stations around the world. There are actually about 50 32-metre dishes that were built for Intelsat in the 60s and 70s that are now around the world, all around the equator. Some are radio telescopes, some are still used for space purposes, some are in disrepair, some are just sitting there. So Goonhilly are looking to try and partner with some of these people to try and build a global network, a private deep space network. And over time, we would build on the basic stuff that we're going to do in this Pathfinder demonstrator, bring in local higher rate comms and potentially optical laser comms in the future, navigation service, etc. And then once we've done all that at the moon, we want to repeat it at Mars. So by this time, 2030 plus, hopefully, who knows if Elon Musk pulls his finger out, there might be a colony on Mars by 2030, you never know. But we want to try and repeat this architecture, as I said, from the moon to the Mars. Now, this is our mission architecture for the first Pathfinder concept. So what we want to do in this Pathfinder is provide 2 services. We want to provide a transportation service to carry other satellites, small satellites, nanosatellites, or hosted payloads to the moon, drop them off into orbit around the moon, and then provide them with a communications relay functionality and TT&C, so forward tasking and payload return. The mission architecture will be a launch into an elliptical orbit. We're talking to a launch provider now, using onboard propulsion on our spacecraft to boost to lunar orbit. We get captured into quite an elliptical initial lunar orbit. It's a polar inclination. We then reduce the orbit down to a lower altitude, and then we drop off other customer nanosats or CubeSats into a dedicated orbit around the moon. And then following this, we then provide this relay service, so a local relay, forward and return, and then a backhaul comms link back to Goonhilly. Overall, what we want to try and do is increase the utilization of these systems. So we want to try and, this first mission, we want to try and take customers with us by offering both the transportation and the comms service, and to show that actually you can do useful things at the moon with very small, low-cost systems. Now, the NASA are sending a fleet of CubeSats to the moon in 2018, hopefully on the first SLS launch. So you can do stuff there with very small satellites, but there's not very many opportunities to get there. And once you're there, you're obviously got 400,000 kilometers to communicate back to Earth rather than your normal 500 to 1,000. So we want to try and provide this proximity link to enable greater utilization of these kind of systems. Here's just some pretty pictures from our mission analysis software, but as I said at the beginning, this is the initial orbit. It's a 76,000 kilometer apogee. We then have some orbit raising phase where we boost the apogee to about 150,000, and then there's a transfer here to the moon. You can see here, and then these squiggles here are the orbit of the spacecraft around the moon in the Earth's reference frame, so it looks a bit strange. And then this is the kind of elliptical orbit that you get around the moon. So the pericenter is a couple of hundred kilometers, few hundred kilometers, and the apocenter here is a few thousand. And over time, the orbit drifts and moves. But we get pretty good coverage over both the north and south pole of the moon with this kind of approach, which is we're assuming to be scientifically interesting. And here's a view of what we think our spacecraft will look like. This is obviously a first concept drawing at the moment, but it's about where the circular ring is at the top. That's the separation system for the launch vehicle, and that's about 1 meter by 1 meter. The spacecraft is sort of about 1.5 meters, 2 meters high. And we've got a UHF array on the front here, so a phased array for providing the communications links, and this will be done at using CCSDS Proximity 1, hopefully. So we need to demonstrate the interoperability between different assets, which is a particular radio protocol. And then we've got 2 steerable X-band dishes here for our Earthlink, and these are on our pointing mechanisms that we've traditionally used for our low Earth orbit missions, and for example the DMC-3 satellites I showed earlier have those kind of systems on them. And body-mounted solar panels deployed here, and then the CubeSats or the nanosats are carried in a bay here and then dispensed once we reach lunar orbit. So we want to carry a fleet of these systems to lunar orbit, and then, as I said, eject them and communicate them with the UHF array. So we have actually, in the last couple of weeks, put out a first call for mission opportunity and payload. So you can find this on Goonhilly website, goonhilly.org/lunar. It's as part of this partnership with ESA, we're trying to establish the customer demand and whether there is a market. We believe there is, but we're actually trying to get a manifest together for the first mission. So we're not asking, obviously, people to sign a contract right now or pay us any money, but we're looking for expressions of interest to help us build our business case. And we've got a dedicated email address, which is lunar@sstl.co.uk. And this is open to anybody in the world who wants to fly a payload up the moon. And the target price would be about £1 million per kilo. So for a CubeSat, something like that, down there, that's rotating on the front of the desk, it would be about £1 million. So I offer it up to you. I think a couple of, quick whip round, maybe have a, fundraising cake sale. That'll be all right. But there is, now I don't know how, for things like, the CubeSats, how you guys would actually go about raising any money. But the opportunity is there if it could be done for an AMSAT system around the moon, or AMSAT-UK system, I should say, around the moon. If you're interested, obviously, as I said, we're not looking for any commitment at the moment, and we're not only offering space for CubeSats, though we have got several people interested in flying CubeSats. We've also got opportunities for hosted payloads actually on our that would remain attached to the main spacecraft. So we've got a couple of people who have had an inquiry from someone, for example, who's interested in flying a biological experiment on the outside of the spacecraft, carrying mammalian cells to see what happens to them in deep space radiation. So we've had lots of different interest in it. So it's not just ejecting CubeSats or nanosats, but also for hosted payloads as well. So anyway, if you're interested, you can download it from Goonhilly website. And there's some supporting documents on there from ESA as well, which they've provided for us. So there's some the radiation analysis and space environment data, the total ionizing dose we expect, the upset rates, latch rates, things like that, as well as a mission analysis document they provided, which shows the kind of coverage you get over the moon, etc. Okay, so that was just a quick blast through of everything we're doing. So just in the way of conclusion, we've got several big projects we're doing right now. Some of them are in orbit, we're now providing a service. Some of them are just about to be launched. Some of them are just starting to be built. Some have been going for years and are still going to carry on for years. But we've got several more exciting ones on the horizon. We're doing stuff in Earth observation, in telecoms, in science, in exploration. And we've got new commercial models for Earth observation. We're doing private sector commercial astrophysics, and we're trying to do commercial lunar exploration. And so it really is LEO, MEO, GEO, and beyond. Thank you very much. I guess I've got a few minutes for questions.
Yes,
we've got a few minutes for any questions, I think, if anyone's got any.
Thanks. Can I ask you about the link budget for lunar communications?
Yes.
Obviously, way beyond LEO. The concept that I've heard reference to is called polarization modulation.
Right.
What can you say about that?
I don't know anything about polarization modulation, to be brutally honest with you. Are you talking about the Earth to Moon, or the Moon to, or our relay spacecraft to the CubeSat?
I'm talking about a signal within that link budget whereby I suspect the signal processing adds a significant gain to
Oh, I see.
the link budget.
Right.
And I mean, signal processing I've seen, for example, in the KickSat sprites,
Right.
which rely on significant processing. But I've also heard the phrase polarization as a form of modulation.
Right.
I would imagine that the two would go together, but I'm asking you the question.
Yes, okay. Our baseline at the moment is UHF and CCSDS proximity 1. So what we're offering is it's not actually on the slides, but what we're offering as part of that £1 million is also you could buy a one-off PC104 software-defined radio. We're talking to our colleagues down the road about building that. That would be offered as part of, so that would be provided to the user if they wanted it. That would interface to an antenna system and to the computer on the CubeSat. That would do all the coding for the proximity 1. Whether that would use some kind of polarization effect to modulate the signal, increase the gain or the link, I honestly don't know. At the moment, I think we're just assuming it's either it's a kind of, our worst case link budget is assuming a kind of whip antenna, linearly polarized, nothing too clever going on, but we want to try and provide something that's a sort of a basic service, omnidirectional coverage. We might look at it in the future. Honestly, at the moment, it's not something that we've considered. Okay, thanks. Anybody else?
Can we ask that you use the microphone for questions so people can hear on stream?
Thanks. How is it on?
Yeah.
How do you do the navigation around the moon?
Well,
Do you rely on the DSN network, or do you set up an own network
Well,
with doing the triangulation and measuring and
we
everything?
are, one of the things that ESA are trying to, well, we're hoping that ESA are going to provide as part of the partnership is the orbit determination and navigation service. So for this first mission, Goonhilly at the moment does not have any ranging capability, although it does TT&C and payload, it doesn't have a ranging setup. So, but ESA regularly range their deep space spacecraft. So we're hoping that ESA will provide that as part of the partnership to provide an orbit determination reference for us. As for providing navigation to the users, what we are looking at the moment is as part of Proximity 1, it has a Doppler mode, so it measures the Doppler shift of the signal as the two spacecraft are moving, and whether we can use that to provide an initial basic navigation service for this particular mission. In the longer term, for the constellation, we want to fly a dedicated navigation transponder a la Galileo. So for the first mission, we don't have enough mass or budget to be able to do both. So we're going to try and do the first one on the basis of ground-based ranging of our spacecraft, and then using effectively our spacecraft as the ground station to then re-range all the other customers. In the future, we would fly a Galileo-esque type navigation transponder, which would just beam a broadcast signal, an ephemeris down that anyone else could pick up. But again, that would still rely on you knowing exactly where the navigation spacecraft is. So we still require ground ranging.
I understand that lunar orbits are not hugely stable.
That's correct.
Would you be flying propulsion on the constellation?
Yes, you'd have to.
What's the lifetime of your satellites?
The kind of orbit we're looking at the moment is about 800 by 8,000 kilometres, so it has the eccentricity orbit's about 0.6. And those kind of orbits are relatively stable in the long term, because they have their sort of average distance they spend away from the moon means that they're not as badly perturbed as other orbits are. So the system we're looking at the moment remains above the lunar surface for at least a year. We will have propulsion on the spacecraft because we've got to do the transfer from the Earth to the moon and then also the orbit modification there. So our baseline mission is to provide the service for a year, and after that we will then probably have to do some small periodic manoeuvres to keep the pericenter of the orbit above the lunar surface. So it can oscillate up and down by quite a few hundred kilometres. So the delta V is reasonably small, it's not too bad, and we could keep the spacecraft going for another 1 or 2 years. But you've also got the radiation environment in that orbit. We want to try and use as we've done successfully for all our previous missions, use as much commercial electronics as we can, rather than the more expensive space grade stuff or really rad hard stuff. So there is a limit to the mission lifetime as well from the environment. But in terms of the orbit, it will be at least a year without needing any active maintenance. Then after that, small periodic manoeuvres. Okay, thanks.
Sorry, I haven't got the microphone. I was particularly
Yeah, I was particularly interested in the Twinkle project.
Right.
I was wondering what sort of orbit that was going to have if it was outward looking.
Yes,
looking at
it's in it's going to be in about between 700 and 800 kilometres. The science team are still debating on the correct altitude in a dawn-dusk circular orbit, so polar inclination, and effectively flying around the terminator between the sun side and the night side of the Earth, and then pointing sort of away, anti-sun always. So it's pointing basically out along the Earth's shadow in a cone around that. So it's always anti-sun. There's an impact on the altitude from stray light coming up from the Earth, which affects the sensitivity of the telescope. But we're going to try and keep it in a low Earth orbit, similar to the environment that we usually operate our spacecraft in to try and keep the cost down. So it's not in a big elliptical orbit like some observatories are. Yeah. Okay.
Okay then.
Lovely.
In that case, thank you very much.
Thank you.
Chris.
Cheers.
I appreciate the
Thank you.
advice on what you're doing.
Thank you.
Can I now invite Graham and Martin's glamorous assistant to come up and join us?